So in the previous lecture, we had discussed a little bit about complete metric spaces, right? Complete metric spaces. So now talking about complete metric spaces. So basically, suppose XD is a metric space and let Xn be a Cauchy sequence, in X. Okay. So if Xn is convergent, then X is a complete metric space. Rather, if it implies Xn is convergent, then X is a complete metric space. In very simple words, we have already discussed a phenomenon that in a general metric space, all convergent sequences are Cauchy, but the converse is not true generally, right? But in the metric space where the converse is true, those specific metric spaces are called complete metric spaces. Clear? So, for example, let's say suppose XD is a discrete metric space. Is a discrete metric space. Okay. So, what are the convergent sequences here? They are the sequences which are eventually constant. Suppose you take a Cauchy sequence, Xn is Cauchy, which is eventually constant, implies Xn is convergent, right? Is it clear? So every discrete metric space is a complete metric space. Clear? Discrete metric spaces are complete metric spaces. Okay. Uh, the real line with respect to its usual metric. The real line with respect to its usual metric is a complete metric space. Okay. Is a complete metric space. Okay. What more can we have? 0, 1 is a complete metric space. C is a complete metric space. C with respect to D. D is usual metric. Is a complete metric space. Sequences in C are of the form Zn, where Zn is Xn plus Iyn. So these are individual real sequences. Okay. Okay. The concepts related to RD and CD, we can extend this for RK, let's say D only, or rather let us not specify the metric, rather RK and CK, these spaces are complete too. Okay. Rather, we have discussed already the form of sequences in RK and CK with respect to usual metric, so you can understand these concepts with respect to usual metric only. RK and CK with respect to usual metric. So what can we say about L1? L1. So L1 was the space of all those sequences in real line such that mod of xi is finite, right? What can I say about L1? Is L1 complete? Let us just see. So suppose we take a Cauchy sequence. Okay? So let xn be a Cauchy sequence in L1, let's say. Okay, xn is a Cauchy sequence in L1. So if so happens, what can we say? So xn is a Cauchy sequence in L1. So from here we can write, therefore x nj, this is a Cauchy sequence in R, is a Cauchy sequence in R, and let's say this converges to some xj for all j belongs to natural numbers. Okay, okay. This is basically the property obeyed by this Cauchy sequence, being a function from n to R. Okay. Now suppose, now let us first discuss the property of it being Cauchy. So xn is Cauchy, right? So xn is Cauchy implies that for all epsilon greater than 0 there exists a natural number n0 such that n and m greater than n0 implies distance between xn and xm is less than epsilon. Okay. Now can we write this as summation um, j equals to 1 to infinity xnj minus xmj, right, and this is less than epsilon. Okay, right, this is the way of defining a metric in L1, right. Now so xnj is Cauchy in R is complete, so it converges to some xj, right. So what can we do here now? So let m tend to infinity. So if m tend to infinity, xmj, this tends to some xj, right. So this implies that the norm xnj minus xj is less than epsilon. This norm is see in L1 this norm xnj is basically the summation j equals to 1 to infinity xnj. Okay. In the first lecture we had discussed these things. What is a norm space, norm linear space, and norm induced metric, and so on. So to avoid this writing this summation symbol, I just use this norm symbol. Okay, so this is this is less than epsilon, right? So if this is less than epsilon, so that means that this sequence, let's say this sequence, xnj minus xj, this sequence, this is contained in L1, and xnj was already contained in L1, so we can say that x, this sequence x, this is contained in L1 indeed, right, clear, because xn was already contained in L1. So this is one thing, and what is one more thing we achieved from here, which is very evident, that is xn converges to x. Very simple, right? And xn converges to x. Yeah. So we had initially considered this to be Cauchy, and we have shown that this is convergent. So what we used here is the completeness of the real line, right? Okay. Next thing, what can we say about what can we say about C00? So if you remember, C00 was basically the space of all those sequences which are eventually zero, right? C00 was the space of all sequences which are eventually zero, right? Which are eventually zero. right? So are they complete? Sorry, is this matrix space complete? So what is the metric associated with C00? So C00 with respect to D forms a metric space when D is the sup norm induced metric, right? Sup norm induced metric. This also written as D infinity. This also written as D infinity. D of xy infinity is given as norm x minus y infinity, which is basically the supremum of all possible xy's. Supremum of all possible xy's. Clear? Clear. So let's check. Okay, suppose you take a sequence xn from C0. Okay. What is xn? Xn is this sequence 1, 1 over 2, 1 over 3, and so on, 1 over n. And this is pretty much evident that this sequence eventually becomes 0 as n tends to infinity, right? So this sequence eventually becomes 0 as n tends to infinity, right? Right? Or we can do one more thing. We can make this sequence eventually 0, let's say. We can make this sequence eventually 0, let's say. Okay. We have made this sequence eventually 0. No worries. Now this is indeed a Cauchy sequence. This is indeed a Cauchy sequence. Yeah. This is pretty much evident from its structure only that this is basically a Cauchy sequence. But xn converges to 0, right? Xn converges to 0. Or rather, it's better to say that xn converges to the sequence 1 over n, right? Xn converges to the sequence 1 over n. This is not the sequence 1 over n. This is the sequence 1 over n. Then we have eventually made zeros, right? So this eventually converges to the sequence 1 over n, and 1 over n is not contained in C00, right? So is this convergent in C00? Not convergent in C00. So it's a Cauchy sequence, not convergent. Therefore, C00 is not complete. Do carefully understand these counter examples. Okay, these counter examples are very necessary. These counter examples are very necessary. Okay. Next, we have a very small topic, and I will give you just a notion. Okay. So what we call function spaces. Okay, function spaces. We have already discussed function spaces in the first 2 or 3 lectures, I hope. So function spaces are basically metric spaces formed using a set of functions, family of functions, right? And the most famous of them is this function, right? Set of all continuous real valued functions with domain closed interval 0, 1, right? So inside function spaces, I just wanna, introduce a notion, which is the concept of equivalent metrics, which is the concept of equivalent metrics. Okay. So I will use the concept of function spaces to explain equivalent metric, but I'm just giving the notion first. So suppose you have a metric space, you have a set X which forms a metric space with respect to metric D1 and with respect to a distinct metric D2. Okay, are metric spaces. Okay, they are distinct metrics D1 and D2. D1 and D2 are equivalent metrics, or we can also write xd1 and xd2 are equivalent metric spaces if for some sequence xn in x Okay, D1 x and x tends to 0 implies that D2 x and x tends to 0 and vice versa. So basically it basically means that if you take a certain sequence from x and it converges to some point in x with respect to one of the metric, then that implies that the sequence converges to same point with respect to the other metric and vice versa. Okay, okay. So basically what I mean is that the sequence xn converges to x with respect to d1 implies xn converges to x with respect to d2 and converse. Okay, so this is the definition of equivalent matrix. Clear? Okay, so a question which is very popular in case of equivalent matrix is that check whether equivalent matrix or not. These sort of question, and one of the questions which is important is that uh, see check whether whether C01 D1 and C02 sorry C01 D2 are are convergent matrix are equivalent metric spaces provided D1 FG is the sup norm induced metric and D2 FG is integral 0 to 1 f minus g dx. Okay, okay. So I'm just writing the answer and giving a hint to this question. I hope you people will try it on your own. So basically they are not equivalent matrices. Okay, D1 and D2 are not equivalent and not equivalent matrix. To check it, what you can do is that take take sequence fnx such that fnx equals to x to the power n and fx as 0. Okay, now d2 f fnf, this will give you 1 over n plus 1, which obviously tends to 0 as n tends to infinity. Well, if you do this in case of d1, you will find that it becomes 1, which does not tends to 0 as n tends to infinity. So I hope you will work out this. So I'm giving you the results. You will write out the problem systematically. Try, at least try. Okay, is this clear? Now we will discuss a few properties related to uh, complete metric spaces. Okay, and then we will move on to further concepts. So a few properties related to metric spaces. Let's say, mm, okay, let us write it as, okay. Let us write the properties only, and then we will be moving on to trace them as theorems. So properties. So suppose XD is a metric space and Y is a non-empty subset of X. So we have already studied that Y with respect to D is also a metric space. We are not restricting the metric at this moment. Okay, it's also a metric space. We are getting the same metric. Okay. This is very trivial. Okay. So now comes a theorem, that is this metric space Y is complete. Complete. Okay, this XD is a complete metric space. So, okay. So Y is complete if and only if it is closed. Okay. Okay. So for a complete metric space, a subset of it is also complete with respect to the same metric if and only if it is closed. Let us check the proof of it. Okay. So let us first, assume y to be complete. Okay. So let y be complete. Let y be complete. We need to show it is closed, right? So for showing it to be closed, we can say that y closure is contained in y. This will do it, right? Right. Y closure is contained in y will automatically imply y closure equals y. So y becomes closed. So let y be complete, and let us take an element from y closure. Okay. Let us take an element from y closure. We have already discussed this thing that the elements from the closure of a set are limits to sequences that belong to the set, right? So that implies that there exists a sequence yn contained in y such that yn tends to x. Okay. Okay. Now, now yn is convergent in y, right? This implies yn is convergent in x, right? 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 Or rather we can directly write that it is Cauchy in x, where the property of Cauchy, right? Yn is Cauchy in x, subsequence property of Cauchy, right? So yn is convergent, so it is a Cauchy sequence in x. So if it is a Cauchy sequence in x, or rather we can use the property that I fumble a lot during these lectures because these are not prepared lectures. Okay, so please adjust a bit. Thanks. Thanks a lot. So yeah, so yn is convergent in y. Okay, so we had assumed y to be complete, right? So we can say yn is a Cauchy sequence. Is a Cauchy sequence. It is convergent. It is a Cauchy sequence. Okay, it's a Cauchy sequence in x. So it's a Cauchy sequence in x basically means it's a Cauchy sequence in y as well. It's a Cauchy sequence in y as well. So this basically means it's convergent in y. Is convergent in y. So it's convergent in y means it's convergent in y means that yn converges to y, and this y must belongs to capital Y, right? Convergent sequences in a set has its limit inside the set as only. So from here we can obviously say that y closure is contained in y, which implies y is closed, right? Right? Clear? Clear? Okay. Okay, so now let us check the converse. Okay, so we assume here y is closed. Okay, so let y be closed. So if y is closed, and we need to prove that a Cauchy sequence in y is a convergent sequence in y, right? So let us assume a Cauchy sequence in y. Okay, so let yn to y be a Cauchy sequence in y. Okay, which implies for all epsilon greater than 0, there exists a natural number n0 such that whenever nm is greater than n0, distance between xn and xm is less than epsilon, right? Right? Now yn is Cauchy in y. This implies yn is Cauchy in x as well, right? Now x is complete. Since x is complete, yn is convergent in X, that implies to yn tends to some x which belongs to capital X. Okay. Now we know that yn is a sequence in Y, so its limit must belong to its closure. That implies to X belongs to Y closure. Now Y is closed, so X belongs to Y closure means X belongs to Y. So that implies yn converges to some point which belongs to Y itself, and it is from here evident that yn is convergent. Convergent, which implies Y is complete. Which implies Y is complete. Okay. So is the proof understood? Okay. Fairly simple proof. Okay. Okay. So the next thing we will be discussing is a decreasing family of sets. Let's say. What do we mean by a decreasing family of sets? So let A be this family an for all n belongs to some n, let's say, or let us make it ai for all I belongs to indexing so capital I is a family of subsets of a metric space xd. Okay, of a metric space xd. So A is said to be a decreasing family of sets if and only if an plus 1 ai plus 1 is contained in ai for all I belongs to indexing set I. Okay, this is the concept of a decreasing family of sets. Is it clear? Is it clear? What does this mean? This means that a1 contains a2 which contains a3 which contains and so on. You have an which contains an plus 1 and so on. Is it clear? Okay. So as we have understood the concept of a decreasing family of set, now we understand the concept of the Cantor intersection theorem. Cantor's intersection theorem. So Cantor's intersection theorem, first let us write the statement. Okay, so let xd be a complete metric space. Let xd be a complete metric space. Let fn, n belongs to n. This is not necessarily natural number set. Okay, it is an indexing set n. Be a decreasing family. Be a decreasing family of non-empty closed sets. Okay, be a decreasing family of non-empty closed sets such that diameter of fn tends to 0 as n tends to infinity. Then intersection n equals to 1 to infinity fn is a singleton set. So basically, the set is something of this sort, this pattern. Okay, the set is keeping on decreasing, and the diameter of the set tends to 0, becomes very small as n tends to infinity, and if so happens, then there is basically only one element common to all these sets. Okay, that is what we need to prove. This is called the Cantor's intersection theorem. Okay. This is very important in real analysis as well. If you understand metric spaces properly, your concepts regarding real analysis also gets very clear. Okay, because they are analogous. While concept of metric spaces, it is far more generalized. When you will be learning topological spaces, it will be more generalized than metric spaces than real analysis. Okay. So these are steps to learn analysis, steps to learn algebraic concepts. Okay. So real analysis is the ultimate result of learning spaces. You have vector spaces. From vector spaces, you went to non-linear spaces. From non-linear spaces, you came to metric spaces. Metric spaces will eventually give the concept of open sets, and we learn topological spaces, which is completely based on the concepts of open sets. Okay. So topological spaces is a more is a wider field. Okay, related to these concepts. Okay. Okay. So let us go to the proof. Let's say. Okay, so I'm again giving the statement, so you can pause the video and write the statement. Okay, proof. So let's say, let f be the intersection of these fn's. Okay, so what does that imply? This imply diameter of f is less than diameter of fn, right? Because f is contained in this sequence fn, obviously, no? So diameter of f is less than equal to diameter of fn. Now diameter of fn tends to 0 as n tends to infinity, which eventually implies diameter of f also tends to 0 as n tends to infinity, which eventually implies there can be at least one element, sorry, at most one element. There can be at most one element in f, right? So f can be a singleton set. So basically f can be a singleton set, or f is a null set. Okay, it can have at most one element. Okay, f cannot have more than one element. So now we need to show that f will have a will have an element in it. So let's try to see that. Yeah. So now see, each fn is non-empty, right? Each fn is non-empty, right? Okay, so let xn belongs to fn. Okay? So if xn belongs to fn, what we can do is that if we show that xn is a Cauchy sequence, okay? If we show xn is a Cauchy sequence, x is the metric space is complete, so xn will become a convergent sequence. If it becomes a convergent sequence, then it converges to some point x, and that point x will eventually belong to this intersection. Okay, this is the claim, kind of. Okay, this is the intuition. So let's see. Fn is non-empty. Let xn belong to fn. So okay. Now xn plus 1, this belongs to fn plus 1, and fn plus 1 is contained in fn, so that implies xn plus 1 is contained in fn. Similarly, xn plus 2 will be contained in fn, xn plus 3 will be contained in fn. So we can say that for all m greater than n, x xm will be contained in fn, right? Right? Okay, right? So basically what are we having? We are having a sequence of this sort, which is contained in fn. Okay, now if so happens, okay, then we can say the distance between xn and xm for all m greater than n is less than equals to the diameter of f, right? Because they lie inside f, right? They lie inside f, and this tends to 0 as n tends to 0. So what does this imply? This implies xn distance between xn and xm tends to 0 as n tends to infinity. So what does this imply? So this implies xn is Cauchy. Okay. Now if xn is Cauchy, so xn is convergent. Xn is convergent since capital X is a complete metric space. Is a complete metric space. So that implies there exists some x belongs to capital X such that xn converges to x. Right? Right? Now, now if xn converges to x, then this subsequence of xn, this will also converge to x. And if so happens, then we say that x belongs to fn for all n belongs to capital, right? Because this x must belongs to fn closure and fn is closed, so it must belongs to fn. Okay, and if so happens, then x belongs to f. F was the intersection of all these f's, which implies f is singleton set x because it cannot have more than one element. Clear? Is it clear? Okay. Okay. Next, we have a very important concept, that is the concept of bare category theorem, rather the concept of what we call bare category. Okay, we will be studying the bare cat. What is bare category now? But the proof of it we will be studying in the next lecture. Okay, I will be covering some other concepts in this lecture. Bare category theorem, it will need a separate lecture because its proof is very rigorous. Okay, and the statement is also a bit confusing to understand. At least when I studied it for the first time, I had a little bit confusion regarding it. So I will dedicate separate lecture, not a lecture only for bare category, but in the next lecture, the first topic will be the proof related to the theorem of bare category. Okay, with details. Okay, so in this lecture we will be covering some other concepts, leaving the proof of bare category theorem for the next lecture. Okay, so let us first just understand what bare category is. Bare category. So we have already learned about dense subsets, right? So I'm recalling it a bit. Suppose xd is a metric space and A is a non-empty subset of X, then A is dense in X. A is dense in X if A closure equals X, right? For example, Q is dense in R. Q is dense in R, right? Okay. Natural numbers are nowhere dense in R. Okay. Natural numbers are nowhere dense in R. So so we basically categorize metric spaces into two parts. Okay, one is called the bare first category and one is called the bare second category. Okay, so let me write here for xd, a non-empty subset of x is said to be of first category if a is a countable union of nowhere dense sets. Okay, example, subsets of real numbers. Okay, and whichever set is not of first category, sets not of first category, sets not of first category implies it is of second category. Okay, okay, 1 minute, guys. Okay. Okay, so the bare category theorem basically says that every complete metric space is of second type. Okay. So BCT, we write it as BCT. So BCT has two forms basically. So the first form of BCT is every every complete metric space is of second category. Okay, so it has one more form, second form. So it says that suppose XD is a complete metric space, let Gn, n belongs to n, be a countable family, of open dense sets. Okay, then the intersection of all these sets is non-empty. Okay, okay. So we will be studying these in the next lecture. Okay, so we move on to the next concept. So it is a very important concept regarding the concept of limits of functions in metric spaces. Okay, so let us study this as a theorem. Basically, let us first give you an insight of what this theorem will say. So it will basically say that when we say na limit, let's say limit fx equals to L as x tends to p. So this basically implies or is biconditional to saying that whenever you take some sequence xn from the domain space, let's say A, such that xn tends to p, then it implies that fxn will tend to L. Okay. So as a function, as the sequence regarding the input space tends to the limit point, the sequence of the images tend to the limit point of the codomain space. Okay, the theorem is like this. So let xd and y rho be two metric spaces, and let phi be a non-empty set from X. Okay, let there be a function from A to Y. So basically, limit x tends to P, fx equals to L, if and only if for all sequences xn in A converging to P in X, fxn converges to L in Y. That is, distance between xn and P tends to 0 implies distance between fxn and L tends to 0. xn is a sequence from A and fxn is a sequence from Y. Okay, okay. This theorem is more specifically useful to show when limits does not exist. Okay. This is very important to show that a limit does not exist. Okay, let us first check the proof of this theorem. The proof, let's say. Okay. So we assume that limit fx as x tends to p equals L, and there exists a sequence xn in A such that xn tends to x. Sorry, xn tends to p. Okay. Acha, xn tends to p. This implies for all epsilon greater than 0, there exists a delta greater than 0 such that uh, sorry, sorry. No, we have basically this, right? So there exists a natural number. There exists a natural number n0 belongs to n such that for all n greater than n0, d of xn p is less than epsilon. Sorry, less than delta. Let me take this as delta. Okay. Let me take this as delta. Conventional method. Okay. Now limit x tends to p f x equals to L. This implies for all epsilon greater than 0, there is a delta greater than 0 such that distance of xn p less than delta implies rho of fxn and L is less than epsilon. So let this be 1, let this be 2. So from 1 and 2 we have for all epsilon greater than 0, there exists an n naught belongs to natural number such that for all n greater than n naught, distance between sorry distance between fxn and L is less than epsilon, which implies this sequence fxn tends to n. Okay, is it clear? Is it clear? Okay, now we need to show the converse. So what does the converse say? So the converse says that if so the converse says that if if there exists a sequence xn in A so that it converges to some x, which implies that fxn converges to L, then limit x tends to p, fx is equals to L, right? Okay, so let's see it. So let us prove the converse. Okay, so in the converse what we have is basically, so we have a sequence xn which converges to x, which implies the sequence fxn converges to it. Okay, now limit x tends to p fxl equals to L be false. Okay, so if so happens, then there exists some epsilon not greater than 0 such that for all delta greater than 0, okay, such that for all such that for all delta greater than 0, there exists some x delta such that whenever distance between x delta and p is less than delta, distance distance between fx delta and L is greater than epsilon naught. Okay, so we are basically taking the the opposite of this limit. Okay, opposite of this definition of limit, because we have considered this to be false. Okay, now what we do is that we choose delta to be 1 over n. Okay, we choose delta to be 1 over n, and we choose this x delta to be xn. Okay, conventionally. Okay, so distance between xn and p is less than 1 over n. Okay, okay, does this imply distance between xn and p, it converges to 0, it tends to 0 as n tends to infinity, right? So xn converges to p. Now we have initially assumed that if so happens, then distance between fx and l, this must converge to, this must converge to, sorry, yeah, so fx must converge to l, so distance between fx and l must tend to 0, right, as fxn, as n tends to infinity, but this is not happening in this case, but this, right? Why? Because here fx n, and distance between fx and n, sorry, distance between fxn and l is greater than epsilon naught. Okay, and when epsilon naught is a positive number, so this is not happening, this is not the case. But we had assumed that this will tend to 0, because we have assumed this, right? We have assumed this, which is implied by this. Okay, so this is happening, but this is not implying this, leads to a contradiction. Therefore, contradiction, which implies limit x tends to p, fx is l. Is it clear? Is it clear? Okay. Is it clear? Acha, in the next lecture, we will be, learning a few, or we will be seeing a few problems where we use this particular concept to check whether a limit exists or not. Before that, I'm giving you a few types of functions which are very important in metric spaces. One of them being Lebesgue function. Lebesgue function. So, a function h from R to R such that h of x equals to 1 if x belongs to Q and 0 otherwise. This is called a Lebesgue function. Okay, this function is a very important one. We will check that limit p, you know, limit of this function as the input variable tends to 0 does not exist. We'll see it in the next lecture. Okay, and then since we have already understood the concepts of or concepts of limit, which we will be further exaggerating in the next lecture, we will be starting with the concepts of continuity in the next lecture. In the next lecture, we will be studying the properties of limits as well as some limit problems related to Lebesgue function. And from the next lecture, we will be first doing the BCT, then the concepts of continuity. So meet you guys in the next lecture.